Continuing our discussion of atoms. All atoms that have the same atomic number have the same number of protons, but there can be what we call isotopes of atoms, which differ in the number of neutrons and therefore differ in their mass numbers. So you should remember the difference between atomic number and mass numbers, right? Atomic number is the number of protons only, and the mass number is the number of protons plus the number of neutrons. So for example, carbon has 3 isotopes: carbon-12, carbon-13, and carbon-14. Carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons, and carbon-14 has 6 protons and 8 neutrons. Carbon-14, you may have heard of, is used in radioactive carbon dating. We use carbon-13 when we do C13 NMR. That's something that we'll learn about in organic chemistry 2. And carbon-12 is the most common isotope of carbon. It's roughly 99% of carbon. So you need to keep in mind what the mass number is. And that will be especially important. Knowing mass numbers will be important when we do mass spectrometry in Chapter 13 in Organic Chemistry 2. Distribution of electrons in an atom. So you guys learned how to write electron configurations, and you still need to know how to write electron configurations, and you need to know how we organize, how we have described the organization of electrons around an atom. So we say that atoms have atomic orbitals and shells. And the first shell is S. And that would be row 1 contains only S atomic orbitals. Row 2 would be the second shell. And the second shell, the atoms have access to S atomic orbitals and P atomic orbitals. In the third shell, this encompasses atoms in row 3. We have S, P, and D type orbitals. And in the fourth shell, or the fourth row of the periodic table, then the orbitals available are S, P, D, and F. The number of atomic orbitals is, if you have only S orbitals, there's only one S orbital. And an S orbital can hold how many electrons? 2. And those electrons have to have opposite spin. They can't be in the same direction. The second shell with the S and P orbitals, anytime we have a P orbital, there are 3 P orbitals. So S orbital, 1, P orbitals, there are going to be 3 of them. When we get up to the third shell, we have 1 S orbital, 3 P orbitals, and then when we have D orbitals, there will be 5 D orbitals. And then on the fourth shell, we'll have our 1 S, our 3 P, our 5 D, and then F is going to have 7 orbitals associated with it. So for each orbital can hold 2 electrons. So in the first shell, the maximum number of electrons is 2. That encompasses hydrogen with 1 electron and helium with 2 electrons. Those are the only atoms in row 1. The second shell, we can have a maximum of 8 electrons, 2 in our S orbital and 6 in our 3p orbitals. So that gives us a total of 8. That's the second row of the periodic table. The atoms in row 2 obey the octet rule. In the third shell of the periodic table, we have rows S, P, and D, or orbitals S, P, and D. So we have 1 orbital for S, 3 for P, and 5 for D. 1 plus 3 plus 5 is 9. 9 times 2 is 18. Atoms in row 3 can have up to 18 electrons max. It cannot exceed 18 electrons. The maximum number of electrons in row 4 is going to be total number of orbitals times 2, and that's going to give us 32 electrons. The first shell is closest to the nucleus, and the closer the atomic orbital is to the nucleus, the lower its energy. It's attracted to the positive charge, so it has lower energy. It's more stable when it's around a positive charge. So the further out we are from the nucleus, the more weakly held the electrons are, and the higher the energy of those electrons. And then within a shell, the energy of the orbitals is going to go from S is lower energy than P, and P is lower energy than D, and D is lower energy than F. So you still have to remember all of the rules that you learned about orbital energy and the order in which the electron configuration is written and why it is written 1s2, 2s2, 2p6, 3s2, 3p6, because the lowest energy electrons are written first, so those are in 1s2, and the highest energy electrons are written last. And remember, our highest energy electrons, or our outermost electrons, are called valence electrons. So remember also the Aufbau principle: an electron goes into the atomic orbital with the lowest energy first, so 1s is always filled before 2s, and etc. Remember the Pauli exclusion principle. Each atomic orbital in a shell, so in a row of the periodic table, we are going to fill those orbitals with no more than 2 electrons, and as we change energy levels, so if we write out an electron configuration for carbon, and we start at the lowest energy, we're going to have 1s2, 2s2, and 2p4. Okay, but this p, when we write out the boxes for these orbitals, it looks like this: 1s, 2s, 2p, and on p we should have 3 boxes of equal energy. Each of the p orbitals is equal. Okay, and so the Aufbau principle, no more than 2 electrons per orbital, and they have to have opposite spin. And then, that's the Pauli exclusion principle. And then we have Hund's rule, and Hund's rule says that an electron goes into an empty degenerate orbital rather than pairing up. So when we get up to 2p, I'm going to bring this down here, and we have 3 degenerate orbitals. What does degenerate mean? This word right here, degenerate. Well, I'll tell you something that might help you remember this. The next time your parents tell you that you're degenerate, you can tell them you're right. I have the same energy as you, because that's what degenerate means. That means they have equal energy. So our p orbitals are degenerate because they have equal energy, and so before we can add 2 electrons in a box, we have to put 1 electron in each box, and that's Hund's rule. I'm actually going to draw these as half arrows. One electron in each box by Hund's rule, and then the fourth electron will be the first electron that pairs. Okay, so remember that rule about Hund's rule, Pauli exclusion principle, and the Aufbau principle. In order, you are going to need to be able to write out your electron configurations. So remembering the order of orbitals, you can use Aufbau's triangle, where you start, you write out the triangle in this way. You start at 1s, and then you go diagonally from each row. So we have 1s to 2s to 2p to 3s, and from 3s to 3p and 4s, and then you go back over diagonal 3d, 4p, 5s, etc. And you're never going to get up to 7f. I'm pretty sure we don't even use 7f like ever. So there are extra orbitals on here at this corner that you're not going to be using. And then once you've written out the order of configuration, what you need to know is how many electrons. Well, so what's the atomic number? Is it a neutral atom? The atomic number should equal to the number of electrons if it's neutral. Okay, so if you know the atomic number, you should be able to say, okay, it has an atomic number of 8. How many electrons is 8? Well, 2, 4, 6, that would be 10. So I don't need to go past 2p because that would be 10. So then where do you stop? You're going to stop at, when you get to 2p, you'd have 2s, and then if we have 8, you'd write 4p or p4. So just remember that for a neutral atom, electrons equal to atomic number. P equals E equals atomic number. For a charged atom, if it's a positively charged atom, you're going to do atomic number minus charge. Let's see if I can write that more neatly. Hey, yeah, okay. And as long as you have the sign of the charge correct, this formula will work for either negative or positive charges. So atomic number minus charge for a cation, right? So let's see, after lithium is sodium, right? So sodium should have, how many electrons does sodium have? Let's look. Sodium has an atomic number of 11. Sodium generally gains a positive 1 charge. So if we have, for sodium plus, we have atomic number 11 minus charge of 1, it's going to have 10 electrons. So then you have to write an electron configuration that has only 10 electrons, okay? Then when you have a negative charge, like, let's do an interesting one, azide. So azide is N3 minus. Nitrogen has 7 electrons. Atomic number 7, I think. Let's go back. Yeah, 7. So we would have 7 so this is for the negative charge. Same formula works. Atomic number 7 minus charge, which is -3, and you need to keep the sign or it won't work. So 7 minus -3 is actually 10 because 2 negatives equal a positive. And so you have to remember to keep the sign on the charge, okay, when you're doing that calculation.